Thank you, Anna. Thank you, the organizers, for letting me delivering a lecture here. It's a big honor and pleasure for me. Actually, Anna and I actually share the office, not only the cities and the labs. So,
yes, yes.
In any case, let me begin with Vibronic Spectroscopy on Photonic quantum computers. And as you can see from the title immediately, that's in a sense a very eclectic talk, which unites elements of quantum chemistry, quantum computing, optics, and technology. And I've been delivering similar talks a few times before to different audiences, and it not always works smoothly because audience has always different level of preparation. And sometimes people found what I'm talking about primitive, sometimes incomprehensible. And I promise this will be the same here. So, but that's inevitable when one talks about things like this. And I apologize for this, for being either too primitive or too complicated. Let us delve into the topic. And actually, before I go on, I'll just start introducing the company I work for. It's HQS Quantum Simulations. H was supposed to be Heisenberg, but the Heisenberg family didn't like it, therefore it's just H. And QS is Quantum Simulations. So we are based in Karlsruhe and work from 2017, being the oldest German software quantum computing company. And our main focus is simulating chemistry and quantum computers, but also on classical computers. And our main product is actually spectroscopy, well, product. Software for spectroscopy, normally NMR, but Vibronics is also what we do. And why we do it? Because we are part of a big FOQuant consortium funded by the state of Germany, the federal government, whose goal is to actually build two Gaussian boson samplers, which are a particular architecture of photonic quantum computers. And the key application for these machines is Vibronic spectroscopy. And we as a software company with competence in chemistry provide data and algorithms. That's the outline of the talk. So as I promised, very primitive things. Vibronic spectra also very primitive. Quantum light, yes. I hope you understand it more than I. And finally, the most interesting part there, what we have done. So that's school physics, classical harmonic oscillator. Why do I show it? Because it has to do not only with molecular vibrations, but also with quantum light. And you all know the harmonic potential and the solutions to the Newton equations, where one can express, one can use canonical variables, position and actually momentum. Velocity is not a canonical variable, sorry for if there are theoretical physicists here, but you see the two components, position and velocity, which have their analogs in electromagnetic waves and in quantum optics. So it's just a brief reminder. So why actually harmonic oscillators? Because how is it had to do with light? Because light is expressed in the harmonic theory. It's very well represented, or actually is harmonic. And the thing is that for quantum computing, one needs to find a good task which maps to your architecture. So if you use light, there you better simulate something which has similar nature as light. And light is photons are bosons and they're harmonic, so why not finding something which looks similar? It can be, say, put into analogy with qubits and with classical computers. You have GPUs and you have CPUs, and you can in principle solve each task on CPUs and the GPUs, but we know there are tasks which better map to GPUs, like training neural networks, for instance, or better mapping to the CPUs with high access to fast memory, that is like integral evaluation or many-body electronic structures theory. So if you want to simulate bosons, then you can use photonic quantum computer. And then you need to understand harmonic oscillators. I think we all do. If we quantize it, we get a very well-known picture with wave functions, which are actually Hermite polynomials with quantized energy levels, with a very well-known 0-point vibrational energy, which will have interesting implications in quantum optics, because at level 0, you get vacuum, but you still have energy, which is known vacuum energy, responsible for many effects like Casimir or Purcell or actually laser emission. And of course, you know that harmonic oscillators are very important for molecules, but only in Born-Oppenheimer approximation. What it is, we separate nuclei from electrons, and then we use our electron cloud as, generating potential in which the nuclei move. And this is a very good model if you use harmonic oscillator for this. So for vibrating nuclei. So here I must disappoint you. When I hear the word vibronic, for instance, I think about books of Isaac Bersuker, for instance, and non-adiabatic couplings, and the so, or Wolfgang Domke, or Sederbaum. But actually, if you just do simple Franck-Condon stuff with totally decoupled electronic and vibrational degrees of freedom, you also get vibronic energies and vibronic spectra. That's a very simple picture, which is actually the case for very, very, very many applications. And it's also not piece of cake, by the way, to compute it. Yes, that's, this was a slide for our managers to tell them that actually molecules are not harmonic oscillators, but they're actually Morse functions, which we know they are not, but for administrative stuff, it suffices. So, which is pretty harmonic, yes, in the lower levels. Yes, that's what we see here. So, if you have polyatomic molecules, that's also very well known. We have 3n-6 modes of vibrations. Each has its own frequency, and each has its own shape. That is the normal mode, and let me show you the simple 3-atomic carbene, CH2. It has 3 modes, exactly the same shapes of vibrations as the water, which will be important for further applications. So 2 stretches up 1 band. Copying from LibreOffice to PowerPoint made irreversible changes to the presentation. So here is the Franck-Condon principle, which was already mentioned. From a ground state of our molecule, we change electronic state to any level of our interest. And then the Franck-Condon principle tells that transition goes instantaneously, which is not true, but it's a very good approximation. And then we arrive not at the minimum of the potential energy surface, but somewhere here up. And depending on where the displacement is, we get excited vibrational levels in excited electronic state. Or it doesn't have to be excited electronic state, it may be photoionization. For instance, if you remove electron and you have the same system of nuclei, but different potential energy surface, because we have different number of electrons here. And the simplest approximation to intensity of this electronic vibronic transition, or vibronic, is given by Franck-Condon factors. So here we have a permanent transition intensity, which has to do with electronic wave function. And this small thing here is the overlap between vibrations here and vibrations here. So this gives the progression. If you look at normal UV spectrum, you see very wide peaks, blobs. But if you have a good resolution device, you will see peaks, progressions, which are exactly Franck-Condon factors. They're defined by overlaps here and here. So we have Hermite polynomials here and there. We need to compute them. That's actually the task which we're gonna solve on quantum computer, photonic quantum computer. So that's the progression we look. That's one photoionization of the CH2 molecule, actually. So yes, in a bad spectrometer, we see this blob. In a good spectrometer, we see a series of lines, which correspond to Franck-Condon factors. Of course, potential energy surface, so this shape of parabola is different for different states. But we can simplify this even more. It's already simple, but we can say why we don't assume that potential energy surface is just displaced. It's the same shape as I plotted here, but it's just a bit wide. In the case of diatomic molecule, it means that it's just stretched, but it vibrates with the same frequency and it's the same shape. Of course, for diatomic, it's always the same shape, but it's just displaced. And what do we get? We just get two displaced harmonic oscillators with identical Hermite polynomials, which are just shifted from one another. And this is called linear coupling approximation. And it's surprisingly good, as we will see. For very, very many molecules, we just compute this displacement and we get a very accurate spectrum. And this is simple because, as you know, as quantum chemists, we don't have to compute anything from the excited state other than its structure. So we just guess where the minimum is, and that's it. We don't need the vibrations to solve vibrational tasks for the excited state. Don't need excited state here, which is a complicated thing. So if there is no displacement, then of course the wave functions are identical. If, say, the displacement is 3, then they are displaced and they are different, and overlaps form nothing else but a well-known Poissonian distribution. So if they're identical in our spectrum, we just see one peak from 0 vibration in ground state to 0 vibrational level in the excited state. If they're displaced, then you see the maximum of this peak is actually to the vibrational state number 4. And this has implications for interpreting the spectrum, because when you just see the blob, you take it maximum, you may assume that it's from minimum to minimum. It's actually not. It's from 0 to 4. And to get the vertical transition energy, you need to subtract 4 electron quanta. But Poissonian distribution is a very simple thing to compute. So we don't need a quantum computer, or it can be done in Python. Even if you have many modes, it's just the spectrum is just convolution of Poissonian distributions. It's very simple computational task. So let's go back to methylene. And this is the photoionization spectrum. So it's actually a tricky molecule which has been studied many times by theoreticians and spectroscopists to get the vertical transition energy. So how did they do it? Quite interesting. So they made a negative ion, CH2 minus, and then photoionized it or deionized it. Then electron was gone and the CH2 was produced in either singlet or triplet state. And from Vibronic spectra, people actually deduced the difference between singlet and triplet. So this singlet triplet splitting by interpreting the Vibronic spectra. But what I wanted to show you is that the Vibronic spectra are very well described by Poisson distributions. And this one reminds us of the picture here. So an ion and singlet CH2 are identical essentially in structure. Therefore, there is no displacement essentially. And we see one peak from 0 to 0 and one small one, which is a progression due to very small displacement. But triplet one is different one. So as I plotted schematically here, the structure of it is different. It's more band than the anion and then the singlet. And this is displacement in terms of normal coordinate of bending, which gives rise to this progression. And the maximum is actually not 0, 0, but 0, 4. So by extrapolating to 0, people were able to define the actual vertical energy. And what was funny is actually that in the experiment, you don't see the spectra separately, you see them together, and then one had to understand which peak belongs to which. Even if you have one here, it may have been from here. So that's how quantum chemists helped to solve this mystery. Maybe not very practical, but very interesting. So Vibronic spectrum here is very simple. It's one Poissonian distribution, more or less along one mode. But one needs to simulate it to understand what it is. Let's become a bit more sophisticated and a bit more realistic. So if our molecules are not just displaced in ground and excited state, but also vibrate with different frequencies, which is not unreasonable to assume, because electronic structure changes, force constant changes too. Then we have a more sophisticated spectrum, which is not a Poissonian distribution anymore. It's called the Picarian distribution. And that's a more intricate computational task. But modes still don't mix, so we just compute a certain number of overlaps between Hermite functions, which have different arguments, not just. So they produce some involved recurrent formulas, but they are still factorized. Therefore, it's not a hard task for computation. What makes it hard is the Dushinsky mixing. So if not only frequency changes and displacement happens, but also the normal modes are different, then you need to consider this. And so if we plot myself and my daughter as modes in the ground state, then excited electronic state can be something like this. And then to compute this overlap in the ground and excited state, you need to compute already two more in the parallel approximation, and you had to do this. So you see, this size is squeezing over the frequencies, these two, but you don't need to consider only these, but also this mixture. So all harmonic oscillators with different arguments overlap with all, and the number grows with the size of molecule. So that's where you would need an acceleration. Let's delve a bit into a stricter theory, and that's not what I showed to the managers. So formally, this Dushinsky equation is this. It's the normal modes in excited state is linear transformation of normal mode in ground state plus the displacement. You know, there were interesting things being done in Soviet Union in 1937, not only we are all aware of, but also the Dushinsky rotation was introduced there. And 40 years in the same place in Moscow, Doktorov and co-workers derived this in a stricter way. So they introduced the operator which relates the excited state vibrations to ground state by by a factorizable threefold operator. And they have all these three effects we were talking about. So displacement, Dushinsky rotation, and this I call squeezing, but it's a frequency change. So you need to do all three. And let us delve into computational stuff. So if we want to compute Franck-Condon factors fairly, that is all overlaps of all vibrational states in ground and excited states, then the scaling becomes more than exponential, depending on the number of modes. And that's where acceleration would be needed, of course. And now, let there be light. We have seen this for classical harmonic oscillation. Now, if you take electromagnetic field and Maxwell equation and solve it, then we also get harmonic oscillator. But now we don't have momentum and velocity. We have canonical quadratures, which are analogous to velocity and momentum in Maxwell equations. Now, it took me half a day to solve Maxwell's equation for vacuum, because I'm not a physicist and I've been solving Schrödinger's equation, not Maxwell's. But it was nice, refreshing experience to understand by personal limitations, but I made it. So very similar to mechanical harmonic oscillator. Of course, we can also quantize it. And then we get quantum optics and not yet quantum field theory. God save us from this. And we have the same harmonic levels, equidistant levels with the same wave functions. But this time they belong to photons and not to molecular vibrations. But good news here is that they're very similar to molecular vibrations. Therefore, we can in principle solve vibrational tasks on photonic quantum computers. Because qubits are spins, they don't have similar physics, but photons do. A bit of fun thing. So in quantum optics, we also use Fock strings, exactly as in second quantization quantum chemistry, which pleased me as a student of Trygve Helgaker. And yes, they have nice properties, energies, harmonic, uncertainty in particle numbers. There is no uncertainty if you have a Fock state light, which is actually hard to generate. But anyway, and the favorite is this uncertainty in electric field, which is for state n not zero. So for state n is this amplitude of E, electric field. So vacuum is not nothing. Vacuum has oscillations. This will have critical consequences actually for quantum computers with photons, since we will be using vacuum levels to simulate something. And let us remember the doctor of operators. They have analogs in quantum optics. So the displacement, which was corresponding to shift in coordinates, is actually a displacement operator, which makes a shift in the phase space for the photon, preserving its noise structure. Sounds a bit abstract, yes. So in reality, if you have a laser beam at a vacuum state is just, waveguide of nothing, and you collide in the interferometer laser beam with vacuum, then you produce, at certain conditions, of course, a displaced state, which has properties of laser, but noise of the vacuum. Long story short, actually, this state would be coherent, the laser state. And coherent state has an interesting property. The photon number distribution in a coherent state is this, which is a Poissonian distribution. So a linear coupling vibronic spectrum. So if one manages to create a beam of photons with this displacement parameter similar to the displacement in the molecule, then you can simulate it. Yes, lasers. Particle distribution, as I said, is Poissonian. So if you create photons which amount the number of vibrational excitations in molecules, then we can actually measure the spectrum. And the linear coupling parameter, displacement is related to this A in quantum optics. Later, I will also use the word B, the letter B, and it's a confusion, but they're all related to one another due to interfield cross-fertilization. Let's put it like this. So how do we actually measure a spectrum in photonic quantum computer? Measuring here doesn't mean chemical measuring, that we take a molecule, put it in spectrometer and measure. That's actually, measure it is actually computation. That's another. So we take our laser sword and then do photon number detection, and that's it. But this man objects. Why? Because laser swords are way too powerful. If you remember, we need to have a few photons only in normal molecules, in normal conditions. We don't have harmonic levels populated up to thousands and whatnot. So we need really, really, really little. Therefore, we use actually vacuum states. In practice, it means we have like very high quality optics with nothing there, so protected from light. And then we apply laser beams to beam splitters and create these laser states with the properties of vacuum. And of course, laser, again, laser. It's an attenuated laser, so laser shines and then it's being cut in intensity multiple times so that it only has very few photons, so that your photon number detectors don't get destroyed. Therefore, this is in fact, to my mind, rocket science, what people in quantum optics do. Let us go to squeezed coherent states. So linear coupling is not interesting. Okay, it is interesting per se, but as we've seen, we don't need quantum computer acceleration for linear coupling because it's Poissonian distribution. So if you go to parallel mode approximation with changing frequencies, then this corresponds to squeezed coherent states of light. What squeezed means, like we don't take a photon and compress it in real space, we modify its quadratures. So in normal coherent state, X and Y quadratures are distributed more or less spherically. And if we modify them, then we get one squeezed and one stretched. So why do we need it and how do we do it? So we shine the light through these optical crystals like KDP, gallium, potassium diphosphate, or lithium niobate. And then from one photon, we get two photons of different frequencies with this squeezed property. So why is it important? Because in quantum optics, people can measure quadratures, either this one or this one. And this one squeezed has way less uncertainty. So for optical measurements, that's critical. We can, by creating squeezed light, one can measure things optically way more precise than without. And this is the most spectacular application, if you can say it in quotation marks, the LIGO experiment. That's how people measured gravitational waves. So that's a huge Michelson interferometer somewhere in Texas, I think, which just, has a standing wave of squeezed light. And as soon as there is a perturbation in space-time curvature from gravitational wave, the diffraction pattern changes, it squeezes, and they detect this squeezed quadrature to have actually seen the wave. So a great business idea for squeezed light application, I would say. But it took me 10 years to understand how it was. This was the first talk I saw in Zurich, because when I joined ETH Zurich, they actually discovered the gravitational waves, and there was an alumni of the university who came and given the talk, and he will say, okay, we use squeezed light. And then it was it. Okay, what is squeezed light? Now I understand, at least generally. But we don't want to use it to measure gravitational waves. We want it for Vibronic spectroscopy. So how? Simple, relatively. So we create vacuum states. We create squeezed vacuum by transferring nothing, vacuum, which is not nothing, through squeezers, and then displace them, and then measure photon number distributions. Which is not yet all, because we actually want to implement Dushinsky rotation. And this is here on the left. This is vacuum, squeezing, displacement, and in between we have interferometer, which mixes the modes. So remember Doctorow's operator, 3 steps, they're here. So interferometer is actually classical Mach-Zehnder interferometer in nature. So it has semi-transparent beam splitters, which can be tuned to transmit certain amount of light and absorb or reflect, sorry. So this is called actually Gaussian boson sampler, and it's not a universal quantum computer, but it can solve Vibronic spectra. So it actually doesn't solve Hamiltonians and quantum mechanics. It really samples this complicated distribution. So one just shines light, passes them through the 3 operations, and measures photon statistics. And from them, one gets Franck-Condon factors. Of course, parameters for all these 3 are taken from quantum chemistry or from your head or from experiments. But the sampling is itself a complicated thing because it poorly scales. And in principle, it promises quantum advantage because here it scales linearly, just number of photons. It's not a deterministic method, stochastics. It's a sampler, but potentially good. And this was developed theoretically by Aspuruguzik and his group 15 years ago and hasn't been realized experimentally until 2 years ago. So by a group from Singapore, and German work on this has begun 2022, which was first a debacle as a huge consortium couldn't even write a report. But then the managers has changed. One of them is talking to you, and it's a stunning success. At least it's very important, so that Federal Chancellor came to the University of Vienna and looked at the chip, photonic chip. I don't know whether it's a good commercial for the computer or not, but at least it's important, you know. So heads up. We have 3 operations for computing Vibronic spectra, and we have photon realization of those. Linear coupling, parallel, mode, Dushinsky, and squeezing, displacement, and interferometer. In the current state, we can do linear coupling. We can almost do squeezing, and this is work in progress. But, of course, we can already measure this, and that's what we did. Let us begin with the photoionization of formic acid. That was the example suggested by Aspuruguzik 10 years ago. And you know, that's my conversation with him on LinkedIn. He was very happy to see that it was finally measured. And this was the measurement from the group of Singapore, from Singapore 2 years ago. Actually, they did the full GBS with 3 operations, and we did just linear coupling. And you can very well see why we did it with linear coupling. Not only because we are lacking the other operations, but because nothing else is needed. So that's a bit strange and interesting, and also sad that people throughout 10 years have been simulating and measuring this molecule without realizing that, I mean, one doesn't need to do it so complicated. One can do it simpler. It's just measuring Poissonian distributions. And let's just look at more molecules. And here it's really a result of measurement in Paderborn. So one is modeling, full GBS simulation, and others are measured. And what we see that most molecules here are well described by linear coupling, except for formaldehyde. So we see here discrepancies, which are actually described by squeezing and by parallel mode. And yes, period design is more complicated. One really needs full GBS. But we have made more molecules and found out that actually linear coupling is good enough for very many applications, which is not a secret for chemists, but I personally didn't know these statistics. So people typically try to do more complicated things to be more impressive. Formic acid. So why actually people use formic acid as example, although they shouldn't use it. So we wanted to understand it, and I think we got it. So this is a Dushinsky matrix, which doesn't look like a unit matrix. So there is considerable mixing here. That's why people wanted to do the interferometry for Dushinsky matrix. Why then linear coupling works if you have a considerable Dushinsky? So because of squeezing. If we go back here to the architecture, we see that in the full device, we first apply squeezing, then interferometry, and then displacement. And if this is vacuum, if this is not producing anything, then mixing nothing with nothing gives us nothing, and only thing which matters is this. So for Dushinsky to have any effect on the spectrum, we actually need squeezing. So if our frequencies in excited states differ considerably from those in the ground state, then we need Dushinsky mixing. Otherwise, we don't, even if it's non-trivial itself. So modes may be mixing, but they won't be seen in the spectrum. And that's exactly the case. These modes are mixed, but their squeezing parameters are next to 0. And considerable are here. Kind of exceptional. The mystery resolved. So we actually observe modes with significant displacement, actually these which are mixed, but mixing doesn't make any effect on them. It's all displacement. It's all linear coupling approximation, which is good. Therefore, we actually achieve better agreement between simulation and measurement because our setup is more pristine. It's just measures things better. And if I show you one more time, that's optics. And the optical loss of photons is terrible. So it's like less than half at most. So photons just go from here to here and they don't arrive where they are supposed to arrive. They are absorbed by the walls, they are lost. And if you do complicated operations here, you reduce your quality. So we actually use more modes. So each channel is a mode and got better quality, which brings us back to the question of quantum advantage, which is vastly discussed in quantum computing community. So if quantum computer is any better than a classical one, and if a vibronic spectroscopy is a use case. And unfortunately, it doesn't seem so. So first, because there's not many applications for that, and most work very nicely with just linear coupling, which doesn't need any involved computation. And secondly, our people have been working on improving efficiency, which is an interesting, I would say, a dialectical story of development of quantum and classical technologies, because people wanted to refute quantum claims, and they did. Actually, based on time-dependent formalism by Barone, known from classical quantum chemistry. So the quest for quantum advantage goes on. Probably it's not here. And with this, I'm about to conclude my talk. So bosonic quantum computers, photonic quantum computers can be useful for vibrations and other bosonic applications, such as vibronic spectroscopy. Technology for quantum optics is really cool, and even if the project didn't achieve any quantum advantage, I think what people did in optics is fantastic. It can be used for quantum communication and whatnot. And we on our side achieved a lot of molecular understanding and made some progress in our more mundane products than quantum computing. So we were able to measure vibronic spectra, or simulate vibronic spectra on real quantum computers for the second time in history and with a better quality. Yes, and don't use your laser sword for photon number detectors, you will burn it. This has now been accepted to NPG Quantum Information. Soon you can read it. And these are the people who are people and institutions invaluable to have this happening. So it's Project FOQuant, University of Paderborn, and my colleagues at HQS from theoretical physics to IT stack. Thank you for your attention.